Hey guys, this is Tech Teach again, and thanks again for watching and paying attention to the videos that we're doing. This video is called Calculating Mechanical Advantage of Class 1 Levers. In this video, we're going to be looking at our teeter-totter example again. We're going to be looking at the different forces that are on a teeter-totter and how to calculate the mechanical advantages. First of all, let's pretend that the amount of weight on the effort side, where these two little girls are, and the amount of weight that is on the load side, where these two little girls are, is the same. We call this term static equilibrium. Static equilibrium is when both sides of the equation of mechanical force, which is this, the force of effort times the distance of effort, the distance from the fulcrum to the effort, is equal to the force of resistance times the distance resistance. Distance resistance would be from the fulcrum to the load. So if those are equal to each other, then the teeter-totter will not move. So we need to be able to look at an example or a lever and be able to tell whether it's in static equilibrium or not. Now, if it's in static equilibrium, then let's say the force of, or the distance of effort is 6 feet. And let's say the distance of resistance is also 6 feet. And let's say the little girls on the left side weigh, say, 60 pounds. And the little girls on the right side also weigh 60 pounds. So if that is the case, then we see that we can plug in the numbers. F of E is 60 pounds, D of E is 6 feet. F of R is also 60 pounds, and D of R is also 6 feet. So you do the math there, you can see that 60 times 6 is 360. And that's equal to 60 times 6, or 360. So that is in a state of static equilibrium. Now, let's change things up a little bit. Let's say that the little girl, and the reason that this little girl over here is having to help out, because this little girl over on the right side doesn't quite weigh 60 pounds. She only weighs 50 pounds. So how much force is the little girl on the right side, who's not on the teeter-totter, having to apply to help the little girl get in static equilibrium, or helping this situation move a little bit? So in this case, we have this setup. We have the force of effort on the left side, 60 pounds, and the distance of effort on the left side at 6 feet. But the little girl only weighs 50 pounds, and she is a distance of 6 feet away from the fulcrum. So we multiply those together and we get 300 on the resistance side, and we get 360 on the effort side. So there's a difference here of 60 foot-pounds. You would multiply foot and pounds together, and you would have a difference of 60 foot-pounds. So this little girl in the screen at the top, if this is the case, she's having to apply quite a bit of pressure to get this thing to move, even though that it's only about a 10-pound difference in weight. And that has a lot to do with how far the leverage is and how long a distance this is. The formula for work is force times a distance. So in this formula you have two types of work. You have effort and you have resistance. That's all the time we've got.